With this lesson, we continue to investigate requirement 1 of battery management systems, which have to do with sensing and control. The particular aspect that we are going to look at now has to do with sensing the presence of a ground fault, otherwise known as an isolation fault. The primary concern that we have has to do with safety. We ask the question, is it safe to touch one terminal, external terminal of the battery pack and the vehicle chassis at the same time? And one possible application has to do with when a vehicle is being serviced. If I open up the hood of the vehicle, as shown in this picture, and if I were to touch one terminal of the battery with one hand and to touch the chassis of the vehicle at the same time with the other hand, would I be safe? Another application would have to do with if I were in an accident and somehow the electronics and the battery pack structure were compromised, would it be safe for an emergency responder to touch the chassis of the vehicle, or you as an occupant, would it be safe for you to touch the chassis as you're trying to exit the vehicle? The high voltage battery should be completely isolated from the chassis, so there should be no problem. And notice that this is quite different from how the 12-volt system is wired in a standard vehicle. In a standard vehicle, the positive terminal from the 12-volt battery is wired independently to everything in the vehicle that requires power. But the ground of the 12-volt battery is wired directly to the chassis. And this is done to eliminate the need for running ground wires to every component in the car. It saves wiring. And it's safe to do so because 12 volts from the 12-volt battery does not have sufficient potential to cause significant injury or harm. It's not safe to do the same thing with the high voltage battery, so neither terminal of the high voltage battery should ever be connected to the chassis of the vehicle. There is a safety standard that dictates the requirement for isolation. The Federal Motor Vehicle Safety Standard, or FMVSS, says that isolation is considered sufficient if less than 2 milliamps of current can flow when I connect the chassis to either the positive terminal directly or to the negative terminal directly using a direct short circuit. This is because it's believed that 2 milliamps of current is less than but close to a lethal threshold. So for worst case analysis, we consider that the resistance of a person might be 0, and if a person were to connect using their body these 2 points, we would want less than 2 milliamps of current to flow. So how to measure isolation? We set up the problem by drawing the schematic diagram shown on the right of this slide. And at the top of the schematic, you can see the high voltage battery and its positive and negative terminals that could be connected to a load. And at the bottom of the schematic, we see the chassis of the vehicle. And ideally, these are completely isolated electrically from each other, no connection whatsoever. I modify the diagram now a little bit to show between the high voltage battery and the chassis, I've added 2 voltmeters and 2 resistors. The resistors model the resistance between the negative terminal in the chassis and between the positive terminal in the chassis. These are not physically present. We don't physically add resistors because that would break isolation. These resistors are shown in the circuit to model whatever resistance is actually present, and ideally that resistance is infinite. I also draw these voltmeters, V1 and V2. And we will actually measure these voltages at some point in our algorithm for checking for isolation. Since we wish for both resistances to be infinite, the worst case resistance is going to be the smaller of the 2 resistors. So we define something called an isolation resistance, Ri, to be the minimum of R1 and R2. And since we require that less than 2 milliamps of current can flow if there's a direct short from one side of the battery to the chassis ground, that means that the remaining resistance must limit this current flow. So by Ohm's law, the isolation resistance must then be greater than the battery voltage divided by 2 milliamps. In other words, it must be greater in magnitude than 500 times VB, of VB is the battery voltage. So our objective is going to be to somehow measure this isolation resistance, the smaller of these two resistances. We don't care about the larger one, we just care about the worst case, smaller one. And to do so, we begin by measuring the two voltages shown in the diagram using a high impedance analog to digital converter that has an internal resistance that's specified usually to be greater than 10 mega ohms. You see, when we're placing these voltmeters in the circuit, technically speaking, we're breaking the isolation that we're looking for. We're making a pathway between one terminal of the battery pack and the chassis of the battery, chassis of the vehicle. But because we specify that the resistance of the voltmeter must be greater than 10 mega ohms, we ensure that less than 2 milliamps of current will flow for most batteries unless the battery voltage is extremely high. And so this is not breaking isolation according to our specification by placing this voltmeter in the circuit. Also notice the polarity indicated on the voltmeters. Both voltages are defined to be positive values, and so when we look at the equations on the upcoming slides, keep that in mind. To continue with the analysis of this circuit, I've first copied the circuit diagram from the previous slide on the top, but I've also redrawn the circuit in a slightly different but equivalent way on the bottom. And if you spend a minute and examine both of these diagrams, you will see that all of the connections are exactly the same, but the diagram on the bottom makes it a little bit more clear that the two resistances form a voltage divider across the battery voltage. Similarly, we see that the sum of V1 plus V2 must be equal to the overall battery voltage. Our objective is to find the smaller of the two resistances, and in a voltage divider, the lesser of the two measured voltages corresponds to the smaller resistor. So if V1 is less than V2, then we must find R1. Otherwise, we must find R2. In the next few slides, we're going to talk about a method that we can follow in order to do this, but before we do so, I first note that we can write that the quotient of V1 divided by R1 is equal to the quotient of V2 over R2. We find this to be true by using Ohm's law and recognizing that I1 must be equal to I2, since that's the only pathway through which current is flowing. And we're going to use these identities in the mathematics we use to solve this problem. We're going to consider two independent cases. In one case, we have determined that V1 is less than V2, and so we must find R1. In the opposite case, we've determined that V2 is less than V1, and therefore we want to find R2. But let's start with the first case. Our next step is to insert a known resistance R0 between the battery and chassis using a transistor switch to close the circuit, as shown in the diagram. So once again, this is going to break strict isolation because we have intentionally made a pathway between the positive terminal and the chassis of the vehicle. However, if we choose this resistor R0 to have a large enough resistance, then we don't actually violate the requirement of less than 2 milliamps of current flowing. So this requires that the resistance R0 be much greater than 500 times the battery voltage. After we've inserted this resistance, we measure the new voltage V2 prime. By Kirchhoff's current law, we know that the current flowing through R1 between the negative terminal of the battery and the chassis must equal the sum of the currents flowing through R2 and through R0 that we've now added to this circuit. So by Ohm's law, the current through R1 is the voltage drop across R1 divided by its resistance. The voltage across R1 is equal to the battery voltage minus this new measured voltage V2 prime. So the current passing through R1 is equal to the battery voltage minus V2 prime, all divided by R1. The current through R2 is equal to its voltage drop divided by its resistance, which is V2 prime divided by R2. The current through R0 is its voltage drop divided by its resistance, or V2 prime divided by R0. Therefore, we have this equation that I've shown that basically says that the current through R1 is equal to the sum of the currents through R0 and R2, or VB minus V2 prime all divided by R1 is equal to V2 prime divided by R2 plus V2 prime divided by R0. We continue the analysis of this equation by substituting the fact that the battery voltage is equal to the previously measured V1 plus V2, and the fact that R2 is equal to R1 times the quotient of V2 divided by V1. We find that V1 plus V2 minus V2 prime divided by R1 is equal to the V2 prime divided by R2 plus V2 prime divided by R0. We can rearrange this by making the substitution for R2 that we have in the last bullet point on this slide. And we find that this is equal to V2 prime multiplied the quotient of V1 divided by R2, V2 all divided by R1, plus V2 prime divided by R0. So we're going to start with that equation and continue on the next slide. So in the last slide we concluded with this relationship, and to proceed we combine all the terms that include resistance R1, which is the term on the left-hand side of the equation, and the first term on the right-hand side of the equation. We bring them all to the left side of the equation by subtracting the term on the right-hand side. And when we do so, we find this result, that V1 plus V2 minus V2 prime times the quotient of V1 over V2 all divided by R1 is V2 prime over R0. We rearrange this equation. The first thing we do is we take the reciprocal of both sides, and then we solve for R1 by multiplying both sides by what's the numerator of the left-hand side as written, but what would be the denominator after taking the reciprocal. We do some rearranging, and we have a final answer that you can see here, that R1 is equal to R0 times the scale factor, and the scale factor is 1 plus V1 over V2 times quantity V2 minus V2 prime all divided by V2 prime. We make this calculation, we find R1, and our final conclusion is that the battery pack is sufficiently isolated if this isolation resistance R1 is larger than 500 times the battery voltage, and that the battery pack therefore is not sufficiently isolated if this condition is not met. So what we've seen in the last few slides is a method for determining the isolation resistance if the initial measurement of V1 was less than the measurement of V2. And the procedure for determining the isolation resistance turns out to be essentially the same if the opposite condition is true, except now we must find R2 in the circuit instead of finding R1 in the circuit, because that will be the limiting value. To do so, we insert a large known resistance R0 between the battery's negative terminal and the chassis using a transistor switch as shown in this diagram. We now measure the voltage difference between the negative terminal and the chassis, which is labeled here as V1 prime. By Kirchhoff's current law, we again say that current through resistance R2 is equal to the sum of the currents through resistor R1 and the current through R0. And using Ohm's law, we convert these equations into voltages divided by resistances, and we achieve this equation that you see here, that the battery voltage minus V1 prime all divided by R2 is equal to V1 prime over R1 plus V1 prime over R0. Our next step, once again, is to substitute the identity that the battery voltage is equal to the sum of the originally measured voltages V1 plus V2, and we also substitute that R1 equals R2 times the quotient of the two voltage from the earlier identity as well, and we achieve this equation here, which is very similar to what we saw in the opposite case. Here we see that V1 plus V2 minus V1 prime, all divided by R2, is equal to V1 prime multiplying V2 divided by V1, all divided by R2, plus V1 prime over R0. To continue, we start with this equation on the next slide, copied exactly. And we combine all of the terms that include resistance R2, and we bring them to the left side of the equation, as you can see here. And again, we take the reciprocal of both sides of this equation, and we solve for R2. And the final result, you can see, is that the isolation resistance R2 is equal to R0 multiplying a scale factor, where the scale factor is 1 plus V2 over V1 times V1 minus V1 prime, all divided by V1 prime. Once again, we conclude that isolation is sufficient if the isolation resistance R2 is bigger than 500 times the battery voltage, and that isolation is not sufficient if that condition is not met. So in summary, in a vehicle application, you have learned that we must maintain isolation between the high voltage battery pack and the chassis of the vehicle. Isolation is considered sufficient if less than 2 milliamps of current can flow if a direct short circuit were to be introduced between either of the battery terminals and the chassis. You learned how to conduct the Federal Motor Vehicle Safety Standard, or FMVSS, procedure for determining the isolation resistance Ri for the battery pack. And the bottom line, you learned that if we follow this procedure, we consider that isolation is sufficient if this resistance is bigger than 500 times the battery pack voltage. That brings us to the end of this topic, and there's one more topic remaining when we look at the measurement and control aspects of requirement 1 of a battery management system, and that's what we're going to look at in the next lesson.